Hi, my name is Avril Sauter and welcome to CCNA Wireless. In this lesson we're going to be talking about the wireless medium itself, and when you look at deploying wireless LANs, it's just incredibly important to understand the basics of how radio operates, because if you understand what's happening over the air, it's going to be much easier for you to understand how to get good coverage, how to get good capacity out of your wireless LAN. So let's start this important lesson. So the first thing we want to talk about is the electromagnetic spectrum. Now, of course, centuries and centuries ago, people have been studying the way that light travels. But it wasn't until Michael Faraday actually noticed that light responded to a magnetic field that we come up with the term electromagnetism. And of course, Michael Faraday is well known in RF circles because of the Faraday cage. So here is a definition of what we mean by electromagnetic radiation. Is the movement of electrically charged particles that create waves of energy, which are then referred to as electromagnetic radiation. Now, when we talk about electromagnetic waveforms, we talk about them in terms of the frequency that they operate at, the wavelength, and also the photon energy. Now, frequency and wavelength are actually inversely proportional, and so frequency equals the speed of light divided by the wavelength. And we talk about frequencies when we talk about radio waves. So when we're down at the lower end of the frequency and we're talking microwave, radio, TV, long waves, we tend to talk in terms of frequencies. How up at the higher frequency levels, when we're talking about gamma rays and X-rays, ultraviolet, visible, infrared, then what we tend to talk about is in terms of wavelengths, but they're actually related. So the higher the frequency, the smaller the wavelength. The lower the frequency, the greater the wavelength. So the photon energy is actually proportional to the frequency, and so up at the very, very high frequencies you actually have the most energy. So something like the gamma ray can have energy of like 1,000,000,000 electron volts, whereas when we come down the frequency, the radio waves have a lot lower energy and we start talking about a femto electrovolt. So the main thing you need to understand from this slide is electromagnetic energy has a very, very wide range from the very high frequencies to the lower frequencies. And in this slide here you can see the visible light, and that we can actually see. But radio waves at a much lower frequency we can't physically see, but they're there. And that's what we're going to use to be sending our ones and zeros over the air. Now on this slide we're going to look at the classes of electromagnetic radiation. And what does that mean? Well, they're classes of usage. Different regions of the spectrum are used in different ways. And again, what we're interested in is this group here called the radio waves. And you can see AM radio, for instance, the wavelength is over 1,000 meters. And so that can actually travel quite far, and the wavelengths are very, very long. As you go up the spectrum and you start getting in to the microwave, you can start to see that the wavelength is about 10 centimeters. Now, why is that important? Is because the way that those waveforms react when they hit obstacles such as walls, your body, your car, will depend on the wavelength. And so understanding the frequency that you're operating on is very important for understanding the effect that frequency has and those waveforms have on the coverage that you're going to experience. In a little while you're going to see that for wireless LANs they operate in a frequency which has a wavelength which is probably less than the size of your hand. And so we're going to build up to understanding that, and again, how that bounces off walls, etc., is dependent on what the wavelength is, and also your antenna design will also vary depending on the wavelength of the frequency that you're using to transmit. So it can be hard to visualize what radio waves are doing, and so here we're just going to go through some of those characteristics. First, the electromagnetic radiation is constantly moving. It travels at the speed of light, which is 3 times 10 to the 8 meters per second. So it's constantly moving. So they do not possess any physical mass. In fact, the term radiation simply means the energy that's being transmitted by waveforms. They do not possess a charge, and they do not require any medium to travel from one point to another. And the interesting thing about radiation is that as it moves and goes through walls and glass and other obstacles, the speed may slow down, but the frequency doesn't change, so it still continues to operate at the same frequency. So when you think about the receiver, as long as you're able to receive on that frequency, you're able to receive that signal. They are subject to the normal laws of reflection and refraction. They can also be absorbed by matter. So just like you feel the heat of the sun on your body and your body absorbs that heat, so it is with electromagnetic radiation. It can be absorbed by different types of matter. And the last one is super important for you to remember. The higher the frequency, the shorter the distance the signals can travel, which conversely means the lower the frequency, the greater the distance can travel. So let's now focus in on the radio frequency fundamentals, and we're going to start using the terms that we use when we described radio waves within the wireless LAN environment. Radio waves are in a specific area of the spectrum band, and we're going to use those radio waves to send our information over the air. And the way we do that is we're going to represent our ones and zeros in waveforms that transmit at certain frequencies. And then by tuning into those frequencies, we'll be able to receive those signals. It's no different than when you tune the radio in your car and you can hear different radio stations. And so we're going to do the same thing. We're going to transmit at different frequencies, and we're going to represent your ones and zeros in waveforms being sent on those frequencies. So when we think of a waveform, there's 3 attributes when we describe the wave. One is the amplitude. You can think of this as the height of the wave. Many people like to think of this when they think about an amplifier with their stereo system. So if you listen to music and you want to turn up the strength of the signal, then you put an amplifier in there and you turn the knob and your signal will get much stronger. And what you're doing is you're creating a much larger gain, a much greater waveform. But the other way of thinking about the amplitude that I always like to give to people is, imagine if you were holding a piece of rope and I was holding the other end, and I made these really high up and down movements with my arm, and I said, when you receive this really big wave, that's a 1. And then if I made some really small movements with my arm, such you've got very small waves coming down the rope, then that would be a 0. And therefore I'm using a form of amplitude to represent my ones and zeros. A big wave, a strong, powerful wave, represents a 1. A little dinky wave, not much power, representing a 0. And that's amplitude. So modifying the amplitude, I can reflect and send you ones and zeros, which is effectively just changing the strength of the waveform. The other thing I can do is I can change the frequency. So imagine, if you were again, that you were holding a piece of rope and I was holding the other end, and I waved my hand up and down really fast, and I said, this really fast wave, that's a 1. And then I waved my arm up and down really slowly, and I said, this really slow wave that I'm forming, that's a 0. And by holding the other end of the rope and receiving the really fast high frequencies and then the really slow frequencies, you would be able to distinguish between my 1s and 0s. Now the phase is a little bit harder to understand, because what I'm going to do is I'm going to change the phase of the wave. So imagine, if you would, you're still holding the other end of the rope, and the first thing I do is I move my hand up and then down, and I say, okay, that's a 1. And for the next time I want to send you a waveform, I move my hand down first and I say, okay, that's a 0. Now if you can detect those phases coming in on the receiver, so you can say, okay, I know that Avril moved her hand up, that must be a 1. Oh, now she's moved her hand down, that must be a 0. And that is changing the phase. So I can change the amplitude, the strength of the signal, the frequency, the number of cycles per second that I'm sending down that rope to your hand, or I can change the phase, where I change, did I go up or did I go down first? And therefore, by changing the waveforms in these ways, I can distinguish between your 1s and 0s. So now you have an idea of how I can change the waveform in order to reflect your 1s and 0s, so I can use waveforms to send information over the air. Let's talk about the major components of a wireless system. So the first thing is a transmitter. And so a transmitter is what's actually going to take your 1s and 0s and actually create the waveforms such that they can go out over the air at the desired frequency. And this is referred to as modulation. So I'm taking your 1s and 0s and modulating them such that I'm creating waveforms which will go out and over the air. An amplifier is just an intermediate device that alters the strength of the signal. Now, if you're very far away, then I obviously will have to raise my power level up in order to get my signal to you. If you're closer to me, then I can reduce down the power. This is very similar to someone shouting at somebody who's on the other side of the field versus someone standing right next to them. They don't need to shout. Now, an amplifier is easy to think about on the transmitting side, but it also exists on the receiving side. When I receive a signal, I may have to amplify that signal before I go ahead and process it. Now, antennas. I love talking about antennas. And antennas are simply electrical devices that take the electrical signal coming from the transmitter and then they convert it into radio waves. On the receiving side, they do the reverse. They take the received radio waves and then convert it back to electric currents and send it to the receiver. The medium, this is what we were talking about a little while ago. This is the physical medium that your signal is going to go out and over. So you're going to radiate your signals from one antenna and they're going to be received at another antenna, and what's in between is what we refer to as the medium. Then of course the opposite of the transmitter is the receiver. This is the device is going to receive those signals from the antenna and then convert them from those radio waves which went to electrical currents, which now have to get back to your 1s and 0s. So receiver's just going to take that and try to estimate and guess what your 1s and 0s were, and hopefully if we got it right, you'll be able to get your data back. Now, a combination of a transmitter and a receiver is called a transceiver. So on this picture here you can see the term transceiver. So those devices both transmit and receive. So let's talk a little bit more about antennas. And one of the most things to realize about an antenna, which a lot of people get confused on, is that antennas are passive, i.e. they don't increase the power or boost the power in any way. What they're simply doing is taking the electrical energy and then convert it to RF waves. However, the pattern that it forms when it propagates over the air is dependent on the antenna. And those different patterns are very important to understand in a wireless LAN. For instance, cover a floor, then you want a circular pattern that's going out and radiating across a floor. If you're trying to connect two buildings, then you want a pattern which is much more of a long lobing pattern, so you want to focus your energy into a narrower beam. Now, when you describe an antenna, those qualities then define how they actually create those radiation patterns over the air. So antennas are designed to operate at certain frequencies. One of the key attributes of an antenna is the wavelength. So a higher frequency, a lower wavelength actually will require quite often a smaller antenna. And then a lower frequency at a higher wavelength sometimes requires a larger antenna, because they're designed to operate at different frequencies and the antennas are designed around the wavelength. When you describe the radiation pattern that's formed, we talk about the beam width. So for instance, if I was wanting to deploy an access point on a wall and maybe I want 180-degree coverage, then I'd want a beam width of 180 degrees. If I was going between buildings and I wanted a narrower beam, then I'd define a beam width maybe of 30 degrees. So we describe antennas in terms of beam width and also the gain. So if I'm able to focus my energy into a narrow beam, my energy is going to go much further, much as if you were talking through a foghorn and you were holding the horn up to your mouth and you speak, your energy goes forward in a forward direction. That represents a gain. So we talk about antennas in terms of beam width and gain. And of course, as you should know with a wireless LAN, your antennas could be internal inside the access point, or they could be external. And so if you're deploying an external antenna, then it's really important that you need to understand how to choose that antenna, how to read those specifications. And so it's very important for external antennas that you know how to read in terms of beam width and antenna gain when you're reading those specifications. So to understand antennas, we need to start with the isotopic antenna. And an isotopic antenna is a theoretical antenna, i.e. it cannot be built. And the reason is that this assumes the antenna is this dot in space and that it's evenly radiating in this perfect sphere. So in every direction that waveform is radiating out and is equal in every direction. And so as it radiates out, that sphere gets bigger and bigger and bigger. And so when we talk about forming patterns and focusing energy in different directions, we talk about it in reference to the isotopic antenna. And that's why normally when we talk about antennas and we look at antenna specifications and we talk about antenna gain, the antenna gain is represented in dBi, i.e. decibel gain relative to an isotopic antenna. Now, so for an isotopic antenna, it radiates out like a perfect sphere. Now imagine if you had a ball and it's a perfect sphere and you put it on the table and you press down at the top. What happens is that it starts to push out at the sides and forms like a donut type shape. So the surface area stays the same, but it forms this kind of donut shape. And that's an omnidirectional antenna. So an omnidirectional antenna has a gain relative to the isotopic antenna, but is forming that donut type shape, and that's what you want if you're deploying an access point covering something like an office area where you want to cover the whole floor area and you want a 360-degree circular pattern, but you don't really want to be radiating down to the floor below or the floor above you. So you create this omnidirectional, this donut type shape, and it gives you a gain relative to the isotopic antenna. Then you have a more directional antenna. If you look at the pictures here, you can see Yagi antennas. This is very much what you'd have, if you had TV at home. I listen to the free radio TV stations, and so therefore I have a Yagi antenna. And I just point it at the various directions until I get the strongest signal, and then I pick up various radio stations. In the bottom right hand corner of this picture, sitting next to the bird, is actually a semi-parabolic antenna. Both the Yagi antenna and a semi-parabolic antenna are what we call directional antennas, and they focus the energy in a specific direction. So like I was saying with the Yagi antenna, I point it in a certain direction, and so it's able to receive more energy coming from that direction. But if there was a transmitter 90-degree angle to it, then I'm not going to be picking up that signal, because I'm really focusing the energy in one direction, and so trying to pick up signals or transmitting energy in that direction with a directional antenna. So another term that you need to be really familiar with is the effective isotopic radiated power, what we refer to as ERP. When you look at regulators around the world, they will regulate the spectrum, and those regulations vary depending on what frequency, what spectrum you're using. And what they typically regulate is the transmit power level from the transmitter, and they also regulate the radiated power from your antenna. And so it's important to understand how to calculate what the radiated power is from your antenna to make sure you're meeting your legal regulatory requirements. So in this picture here, I've got my transmitter, and let's say my transmitter is transmitting at 20 dBm. For those of you not familiar with dBm, we will be discussing that in a little bit more detail a little bit later on. But 20 dBm is 100 milliwatts. So if I'm transmitting at 20 dBm from my transmitter, and then that signal is going up the cable to the antenna. Now, as it goes through the cable and the connectors, it's going to suffer some loss. And so let's say I get a 1 dB of loss. I have to take that away. So that would be 20 dBm minus 1 dB. Then I get to the antenna, and let's say in this example I'm using a parabolic antenna like the example shows, and let's say the gain of that antenna relative to my isotopic antenna. So remember, my isotopic antenna is that perfect sphere, but here I'm forcing all my energy with a parabolic dish into a long beam. So let's say I have a gain of 15 dBi. Then my effective isotopic radiated power would be my transmitter, which was 20 dBm, minus my cable loss, which was 1 dB, plus my 15 dBi antenna gain. So there's 20 minus 1 plus 15, which is 34 dBm. So in this scenario, I would have to make sure that the frequency I was operating on would allow me to both transmit from a transmitter at 20 dBm, i.e. 100 milliwatts, and my effective radiated power was 34 dBm. Now I want to focus in on the frequencies that are used by the wireless LAN. And wireless LAN is the most common technology worldwide, and so when we talk about the specific frequencies of wireless LANs, we're talking about the US and Europe and Asia and Australia and Africa and the Middle East. They're all using the same frequency bands. Now previously you saw that the spectrum band varied from the very low frequencies to the very high, all the way up to the gamma rays, and we said, okay, these are the radio waves. Now when we look at that spectrum that's focused around the radio waves, it's actually split up into different chunks, and those different chunks are given different names, and those names vary between different countries around the world. So here we're looking at a slide which is from the United States. And so the United States, the Federal Communications Commission, the FCC, have defined the industrial, scientific, and mechanical bands. Right? And you can see these are defined for specific usages. And then within that can be broken down even further, or you could have some bands which have multiple names and different usages in them. And so it's important here to recognize that you'll sometimes hear certain names for certain bands and that they vary in different countries around the world. And I might say we're deploying the wireless LAN in the 2.4 gigahertz band, and that band may be called the ISM band in North America and will be called something else in Europe. Now, I know you've all been waiting to find out about the frequencies that the wireless LAN's been deployed in. So this one of two frequencies is most common. This is the 2.4 gigahertz band. This is where your 802.11b was deployed. So this is very, very popular, very, very widely deployed worldwide. But it's not only 802.11b that was deployed in this band. Your microwave oven also operates in part of this band, normally up around about the 2.45 gigahertz band, so slightly around the middle of the 2.4 gigahertz band. You'll find cordless phones in this band. You even find some car alarm sensors. Some of the other more common things you'll find here will be things like Zigbee sensors, if you've heard of the Zigbee standard. Also, your Bluetooth operates here. If you have a Bluetooth headset operating with your cell phone, that Bluetooth headset is operating in this band as well. So what does it mean if you've got microwave ovens and you've got cordless phones and you've got wireless LANs and you've got Bluetooth headsets operating in the same frequency band? What it means is that they interfere with each other. And so the wireless LAN technology was actually written and defined to actually coexist with other technologies that are operating in that band. But the more interference there is, then the more the impact will be on the performance of your wireless LAN system. And we're going to talk a lot more about that later on. The other band that is being increasingly used is the 5 gigahertz band. Now, 802.11a is deployed in this frequency band, but it really wasn't very successful and it really didn't catch on very much, and people preferred B and G, which operates in the 2.4 gigahertz band. And the reason is what I mentioned to you earlier. Up in the higher frequency bands, the signals don't go as far. They attenuate more, i.e. the signal doesn't go as far, therefore I can't have as good as coverage as I can in the 2.4 gigahertz band for the same transmitted power. And so a lot of people prefer the 2.4 simply because the coverage is better. Now the 5 gigahertz band also has other technology that operates there. You'll see, for instance, other types of cordless phones that have emerged. I've seen baby monitors up in the 5 gigahertz band, so you will see other sources of devices that interfere in this band as well with your wireless LAN operations. But typically this band has less noise in it. So for instance, I was at Train Signal a couple of months ago, and I was looking at what wireless LANs were operating in their corporate head office, and I didn't see any noise in the 5 gigahertz band. Everybody had deployed their wireless LANs in the 2.4 gigahertz band, and I could see the microwave ovens and the cordless phones, etc., operating in that band. But the 5 gigahertz band was absolutely clear in their corporate location. And so quite often people will say, why don't I deploy in the 5 gigahertz band? Yes, the coverage isn't as good, but I have a cleaner environment, less subject to interference and noise caused by other devices. Now, simply as an FYI, Cisco doesn't currently have any products that operate in the 700 megahertz band, but there are a lot of discussions about Wi-Fi in the 700 megahertz band. There are products out there, and they're sometimes called super Wi-Fi. So you can have Wi-Fi operating in other frequency bands, but for the CCNA wireless course and the focus on Cisco products, you can really focus in on the 2.4 and the 5 gigahertz bands. Now in this demonstration, what I'm going to do is just pull up some specifications and take a look at them and show you how Cisco define their products to operate at different frequencies around the world. And it's very important to know this, because when you order your Cisco products, you order them to be deployed in certain markets. You cannot just take a product that's been built for deployment in the US and take it to Europe, because the frequency bands are slightly different. And if you take that access point and deploy it in Europe, you may be breaking the legal regulatory requirements. And so it's very important just to be sensitive and make sure you're buying product which is appropriate for the region of the world that you're deploying in. So let's take a look at some of those specifications. Well, the product I wanted to take a look at is the 1040 series access point. This is one of my favorite Cisco access points. It's for deployment in a small business setting. It's an entry-level 802.11n device. Up here you can actually see the name of the datasheet should you actually want to pull this and take a look at it. Now what I want to do is I want to look at the features and capabilities that we've talked about in this module. Now at the end of the course you should feel comfortable at looking at all the specifications for Cisco's wireless products. Here we're just going to take a look at an access point features that we've talked about at this time. So let me come down, and the first thing I want to show you is the part number. So you'll notice here the part numbers here have this X in them. Now this X stands for regulatory domain. So depending on which country you're deploying it in, you would find a product with a part number that was specific for that country. And so if we come down a little bit more, you can see here the actual regulatory domains, what the letters are. So you can see here letter A, C, E, etc. Now I happen to know letter A is for Canada and North America. So I know that if I was buying a product for North America, it would have the letter A in it and it would operate in those bands. Now if you're not sure what letter you are, i.e. what your regulatory domain is, there's a document that you can take a look at. This document is called the Wireless LAN Compliance Status, and when you pull this document, always make sure that you do have the latest document, and this really covers all of the wireless LAN products that Cisco is shipping. And again, up here, the data sheet, the product data sheet number I've included for you, should you want to take a look at this. Now, if you come down, it's got different products here, depending on what my product is. So I'd click on that if I'm deploying an N access point or maybe a mesh access point. And then what you have is you have a list of countries. So if I come down here, you can see country A is Canada, and the US, as I mentioned before, Mexico is N, and I can scroll down and find the country that I'm interested in for my Pacific product. So again, if you have concerns about not knowing your regulatory domain for your Pacific country and how Cisco number that, this is the document you want to be taking a look at. But the main thing we wanted to show on this demo is the fact that your access point will show the regulatory domain, and you need to buy the product for the right regulatory domain, the country you're deploying it in. And if you do that, then that product will conform to the regulatory and legal requirements of that country. If we come down a bit here, there's a couple of other things I wanted to show you. One is here is the transmit power, and just below that we have the antennas. Now this is an integrated antenna in this particular access point, so I don't have to worry about calculating my ERP and making sure I'm within the legal limits of my country, because Cisco's taken care of that as long as I buy a product with the right regulatory domain in it. However, if I did have external antennas, this is where I'd be looking. And here I'd be looking at my transmit power, and you can see here in the 2.4 as well as the 5 gigahertz band, and you may see some difference there depending on the product and what country you're deploying it in. And then down here, this is an internal antenna. If I was using an external antenna, I would see the same types of specifications, and you can see there's an antenna here for the 2.4 gigahertz band, an antenna for the 5 gigahertz band, and you can see that they have different gains. In the 2.4 gigahertz band, I have a 5 dBi gain. In the 5 gigahertz band, I have a 3 dBi gain. So again, if I was using external antennas, I would look at my transmit power and my antenna gain to make sure that I'm underneath my legal requirements for ERP. And again, we don't need to worry about that for Cisco product because they've already taken care of that as part of their product. Also notice here we talked about the beam width, and you can see here this is a 360-degree beam width, which tells me that this is an omni antenna. So think about this. I've taken my isotopic antenna, that perfect sphere, and I've squished it down to form this donut shape, giving me 360-degree coverage across the floor of my building that I'm deploying it, and giving me a 3 or a 4 dB gain depending on what frequency I'm deploying it on. So this would be deployed on the ceiling and then giving me a radiation pattern of 360 degrees. I'll mention this to you now. Never take an access point like this and deploy it on the wall. This access point has been designed with this antenna to give you a 360-degree coverage when deployed on the ceiling. If you take it and deploy it at right angles on a wall, then what's going to happen is your 360-degree coverage will be covering the floor down below and the floor above, and your coverage going horizontally will not be very good. So remember, when you see an antenna like this, see an access point like this, this is for deployment on the ceiling, because that's where you've got coverage, that's where you've got your antenna gain. So again, start to read these data sheets. Very important that you start to understand and relate to the Cisco products. Here we've taken a look at a couple of features. As we go on in the course, you'll become more and more comfortable with the other technical aspects which are on these data sheets. I hope you enjoyed this lesson. Come back and join me for the next one.